In my first lecture, I have specified what is analysis of algorithms and what is design of algorithms. After design of algorithms, then it is very much essential to analyze the algorithm to judge which algorithm is best algorithms. Now, how we will represent the analysis result? For this purpose, different asymptotic notations are used. The asymptotic notations which are very much popular, these are big O, theta and omega. Today, we will discuss in details how those asymptotic notations are used to represent the analysis result. Those asymptotic notations are very much useful. They are very important tool to represent the analysis result. Let us first write a very simple program, and then we will see how those developed programs or algorithms can be analyzed using some convention. Let us consider this problem. Suppose we want to find out the sum of the series 1 plus 2 plus 3 plus dot dot n. Here user input will be n. N will be inputted from the user. Like we are writing in this way, procedure. Let us call this name of this procedure is sum of series, and the argument which is passed from the user is n. Begin. I am using a notations which is not pardon to any particular language. I am using a syntax free notations to represent this so that it can be easily understood. So I am declaring a variable integer I. I am setting a loop for I is equal to 1, I less equal to n, which is inputted here, I plus plus, and I am taking another variable for sum s, which is initialized with 0, and I am writing this s is equal to s, initial value of s plus I, and for, and at the end of this thing we will return s, and end of the algorithm, end sum of series. So it is very intuitive and very easy to understand that there is an iteration, repetitions, that loop starts from 1 to n, and every time that value of I is added with the initial 0 value of s, and at the end of these things it will return the result. Now let us analyze these algorithms to decide how much time it will take. Here we are not interested to calculate the exact time, because it is not possible for us to measure the exact time. That depends on so many other factors, like in which computer the program is running, what are the processor speed, what are the memory bandwidth, what are the type of the operands. So there are so many factors by which the exact time depends. So we are not interested for the exact time, but we want to find out how much time in terms of the input parameters it will take in terms of some notations, and these notations are basically asymptotic notations. Let us see, and for this purpose we need to calculate how much basic steps are required, because we will use that each basic steps that requires 1 unit of time, and that unit is no unitless, because we will consider that 1 unit means 1 count. Okay, we are not considering what is the absolute value of this unit. We require to find out how many count are required. Let us understand that. In this case, assignment of 0 to s, that is requiring 1 unit of time, because that is the basic step, 1 basic steps. Every iteration of this for loop is a basic step. So that will again one count. This assignment and addition can be considered as the basic steps, so that is also taking 1 unit of time. And this return statement, that is also basic steps requiring 1 unit of time. Now let us understand how much units of times are required, total how much count are required for this procedure. This assignment, 0 assignment, is taking only one page, so this takes 1 count, total 1 unit time is required. Now this for loop, every iteration is requiring 1 unit time. How many times this is iterated? N times, n unit, that is n times. For every iterations of this loop, this statement is executed, so this will also take n times, n unit times, and this return statement is executed only once, so this will take 1 times. Now total count for this unit is 2n plus 2. So if I say that Tn is the total time consumed by these algorithms, total unit time is consumed by these algorithms. So Tn can be said as 2n plus 2 roughly. So in this case, it is very clear that the total time is depending on the value of n, and this constant does not matter, because our assumption here is no absolute value of this unit. We are not interested for this absolute value of this unit. We are interested for the count, number of basic steps, because our assumption is all the computers, all the platforms on which the algorithms will run, that is uniform. Because we do not know in advance in which computer these algorithms will run. So to compare the efficiency of algorithms, we are assuming that all platforms, all computers are uniform, and this model is known as unified machine model. Unified machine model. And in this case, we are not interested for the absolute value of this unit, we are interested for counting the number of basic steps. And another important thing is this constant is not important, because we can say that the total time is depends on n. This 2 doesn't matter, because why this 2 doesn't matter? Because we can consider this unit can be larger, maybe larger for other computers. So this is not matters. It is very intuitive that the running time is depending on, is proportional to n, not dependent on this constant. Now let us consider another problem, that is to find the sum of 2 matrices. You know that matrices are nothing but 2D array. Suppose this is one matrix, 1, 5, 7, 8. This is A. Let B is another matrix, say 10, 12, 3, 16. Now we can sum up 2 matrices provided their dimensions are same. And what will be the algorithm for this? That is, sum the corresponding positions element, that is, this element is summed up with this, and that will be stored in the result matrix C. So this plus this is stored in these positions, this plus this is stored in these positions, 7 plus 3 is stored in these positions, and 8 plus 16 is stored in these positions. So what is the procedure for doing this? What are the steps? We have to access every element, and the corresponding row column positions element are summed up and stored in the corresponding positions of the result matrix. Now let us write the procedure for this. So in the same way we are writing procedure. Let us call this as add matrix. add matrix. And what are required to be passed? A, B, and C will be declared locally, and that will be returned. So we are declaring 2D array like integer A. I am calling this A, small a. This row column will be specified from the caller, and B, this is also a 2D array, and int n, where n is considered as the dimension of the matrix. I am considering for simplicity the square matrix. So the matrix will be n by n. Begin. So we are declaring a local variable as int c, say specified dimensions, and I am declaring I, j for accessing row and column, and we are setting a loop like this for I is equal to 1, I less equal to n, I plus plus, for j is equal to 1, j less equal to n, j plus plus. So for each ij positions, what I am doing? I am summing up a and b and store in the C array, that is Cij. There we are storing Aij plus Bij, and for n4, and at the end return C, and end of the algorithm, end add matrix. So this is very simple algorithms and very easy to understand. Now let us apply the same analysis technique. Every iteration of this for loop is the basic steps, so requiring 1 unit of time. Every iteration of this for loop, J for loop, is again a basic steps requiring 1 unit of time. And this addition and assignment is also a basic step that is also requiring 1 unit of time. And this return statement is also a basic step requiring 1 unit of time. Now let us count how many times this for loop is executed. That is for I is equal to 1 to n, and then assignment. I am considering this, all these steps will be a count, that is it is requiring total n count, that is n unit of time. Okay, n unit of times. Now how many times this will execute? For every iteration of this will execute. So all total this will iterate n square times, n square unit of time it will consume. And how many times this will be executed? Again n square unit time it will consume, because it will be for every iteration of this will be executed, so it will also take n square unit of time, and this will be executed only one. So this will consume 1 unit of time. So in this case, if I say Tn is the total time consumed by the algorithms, again here the time is the number of units. We are not interested for the absolute value of this time, because it is not possible for us to calculate. So the total unit is 2n square plus n plus 1, 2n square plus n plus 1. In the earlier programs, we have calculated the time as Tn is equal to 2n plus 2, and here this is 2n square plus n plus 1. So if I compare these two problems, then it is very clear that this algorithm, this is matrix addition, here the running time is dominated by this term n square. So the number of units consumed to complete this execution is proportional to n square, not n. But in the sum of the series for n natural numbers, that is proportional to n. So here is the concept for asymptotic notation comes. How the different algorithms behaves, how different algorithms are compared in terms of the input parameters, considering all the platforms are uniform. So this is the notations, and it is asymptotic because we are interested to know how the algorithm behaves for larger value for the inputs, for larger value of n. So n is very large. We are not interested for small values of n because it may behave differently for smaller values, but we are interested for larger values of n, and the constant are immaterial because here this constant is dependent on the internal architectures of the machine. So we can consider that constant are dropped in this asymptotic analysis. Now let us formally define the different asymptotic notations, and before that I will just take a couple of minutes to discuss different constructs which are required for analyzing any structured algorithm, because we know that any structured algorithm is basically based on 4 constructs. These are sequence, selection, iteration and function call. So if we can develop suitable methodology to analyze these 4 constructs properly, then we can analyze any developed algorithms, because any algorithms ultimately consist of these 4 constructs. Now let us see how we can apply this analysis notation, analysis construct to analyze any developed algorithms which consist of basically these 4 constructs: sequence, selection, iteration and function call.